Our penultimate speaker is Tom Czartoski, who's the founder of Solution Recovery Services, a provider of fluid management and fluid recycling services based in Dexter, Michigan. He's also the CEO of United Solutions, Inc., a holding company with 150 employees and $30 million in sales with over 3,000 clients. Tom's received his bachelor's in environmental chemistry from University of Finland and his master's in civil engineering from Tufts University.
All right, thank you. Okay, a little bit about, I'm Tom Czartoski, as I just introduced, a little bit about SRS. I guess as I could explain, we're headquartered out of Michigan. We're a separation and purification company. We're about 13 years old. We grew from 1 person to 160 people and operate 5 different facilities throughout the Midwest. Active with building, our group likes to cut steel, right? Likes to build process systems and put separation purification systems within clients' operations. So we have those operations in 3,000 customers throughout the Midwest, operating in about 13 states. So our entree into the alternative fuel space was extracting corn oil out of dry mill ethanol plants, and that was an opportunity to evaluate an aqueous slurry that was a high protein content slurry and a lipid that was really entrained, and the protein acted as a detergent and held that lipid. And we evaluated alternatives to get that lipid to aggregate and separate, and learned a lot about that effect during that process. So about 3 or 4 years back, we started a program to take a look at algae and see if we could apply the same principles and skills to algal biomass and process it in a wet way. So once we started looking into the challenge, we viewed it more as a lipid, protein, and carbohydrate gain, knowing that, we started off as just lipid extraction, but realized that, oh my goodness, if you have 40% by weight lipid and you have 60% by weight other stuff, in a very large-scale operation, that's a lot of material. So what's going to happen to the carbohydrates and what's going to happen to the lipids? So we set out to build a process that really key on our list was net positive 80% energy. We didn't want to burn a lot of energy to get energy out. We wanted a process that was reasonably flexible or algae agnostic, able to handle phototrophs, mixotrophs, heterotrophs, and different strains. We really wanted to partition all of the metabolites, or at least 90% of the metabolites, and get likes with likes. If we could get the proteins in one bucket and get the carbs in another bucket, and get the lipids in a third, we thought that would be fantastic. We wanted to recycle the nutrients. We thought the nitrogen and phosphorus was important. The nitrogen is a whole different challenge, but I'll get into that later. But the phosphorus was pretty important, specifically converting it from an organic phos to an inorganic phosphate. We needed a refinery-style scalable operation. This had to be big reactors. It had to be from pulp and paper or refinery operations. And lastly, you can't just get the backbone lipids, right? A lot of great pictures up there about all these great bubbles of oil, and geez, you just bust this thing open, the oil's going to pour out. Well, you know, we're active with about 16 different algae firms that send us open pond and enclosed heterotrophs, and very few actually have big goblets of oil that'll just spill out. So you got to go after that cell wall containing lipid. Just a real quick view of our process. It's a 4-step process. First, we condition the biomass. We need to get the polysaccharides off the cell walls and into the polar phase. We then extract. It is solvent assisted, although it's a wet process. In order to partition the polar and the non-polar phases, we use an organic solvent to partition. And then we recover the chemistry as well as the heat, as well as any of the solvents used in the process. In the end, we make 3 buckets. We make a lipid bucket, we make a high protein bucket, and we make a carbohydrate bucket. Energy balance, very important. This is a very simplistic view of our energy balance, but on the left, you have a wet mill dry hexane extraction process. It's the only one, sort of the benchmark that we can compare to. Of course, right off, if you send a 13% paste into wet milling and you're drying and pelletizing, you use a ton of energy, not just the intracellular, but all the dehydrating all the moisture. And then next on to extraction and solvent recovery. In our experience in running that process, we tend to be on an average of about 20–25% yield. On our process on the right, 100 kg ash-free dry weight at 13% ash-free dry weight. First, extraction and solvent recovery, 95,000 kilocalories, but a 40% yield, a much higher yield in that process. Actually, drying tends to inhibit our extraction. So next, dewatering. If you want to dewater the residual meal, another 46,000. So in drawing your attention to the bottom, a difference of 224,000 kilocalories versus 142 for 100 kgs of ash-free dry weight. So significant energy difference. And lastly, then on the bottom, the percent dry weight. So on our side, the dry biosolids are only net 32% energy, but if you leave the slurry wet and you find a source to use it, we have reached the goal of net 20%. So this is a very simplified mass balance because it gets really challenging to explain the notion of partitioning into three buckets. But in the top center, you have 100 grams coming into the process. That 100-gram algal biomass is 40% oil, 36% protein, and 18% carbs, 6% other. You go into the fractionation process, you come out with three buckets. So every time we run for a client, evaluate a biomass, our goal is to get these partitions, get all the carbs into the far right, get all the lipids into the far left, and the proteins in the middle. So on the far left, you get 37% of the 37 grams of the 100. In the middle, you have the proteins at 45, and on the far right, you actually have 17 grams of biomass partitioned to a polar phase. Specifically, very high in the carbohydrates, some ash, and both of those don't have value in the residual meal. They do have value if we can partition and keep them separate, of course. The starches, the polysaccharides, and if we can make any monomer sugars. So specifically now about the lipid phase. On the lipid phase, most of it's going to be triglycerides or fatty acids. In this case, this is an average over hundreds of samples and over 14 different clients. The triglycerides being, and by the way, this is photosynthetic algae, 73% being triglycerides. So the remaining compounds, the phospholipids, the sterols, the carotenes, chlorophyll, comprise the rest. And what to do with that? Well, I won't spend much time on the triglycerides. Of course, we all know about the omega-3 and all those wonderful peaks on that side and fuel conversion alternatives. On the right-hand side, you can take this additional stream and concentrate the tocopherols, right? The stigmasterols, the sterols, very valuable compounds that if depending on the market conditions, and purify and isolate those compounds. We've been working on a process to aggregate that 20 or so percent and go through a treatment process to break those compounds down into alkenes, and aromatics. And specifically, you see a chromatogram down on the right that illustrates toluene, xylene, and mono and dihydride substituted aromatics. So some fantastic compounds that can come out of those, generally called unsaponifiables. So we like the unsaps. We get criticized when we send downstream people, they want 100% fatty acid. Well, I'm here to tell you, physiologically, those algae need these unsaps, and they're going to be there if you're growing photoautotrophically. And they're fantastic compounds. Here's a view again of the polar fraction of that 17 grams we spoke of. 60% of them are going to be in the carbohydrate fraction. Following the arrow down to the left, of that 60%, we're reducing into monomer sugars into glucose, 61% into glucose. We basically at this point are stopping there in terms of our process, but those are very interesting partitioning and concentration. Down on the right, you could aggregate all of this water stream that includes the proteins, the broken down amino acids, the phosphate, and the sugars, and use it as a growth media, or use it heterotrophically, use it as a fermentation alternative. And down on the bottom right is a chlorella vulgaris example compared to an F2 media. The water that we produce post-extraction grows heterotrophically in a fantastic growth media. Moving right along now to 300 different samples that we've processed, ranging yields from 4 to 74 on the left, and your energetics, the amount of energy, kilocalories per kilogram of algal biomass, really decline as your oil yield goes up. So on the graph on the left, these are from, again, a variety of clients. Towards the top, anything above 50% tends to be a heterotroph. On the bottom, you have your photosynthetic phototrophs. So as you get into 60-70% oil, your energy goes way down. It's fantastic. What we call our crush spread then, about co-products. So it isn't a matter of what's it cost you to extract my oil. No. It's a matter of, I've got a ton of biomass, what can you make out of it? And in order to evaluate that, we have to evaluate it in the context of the value of the streams that we're partitioning and the cost it's going to take to accommodate that. So in this example, we work with our clients to develop a very customized product suite depending on what they want to do with their streams, if they want to use the sugars as heterotrophic feed, or if they want to separate the omega-3, create this crush spread. About our program a little bit, clients send us samples, we bench scale analyze it, we provide analytical, we model out the whole process energetics, we toll process for them, producing gallons of oil, and then we build a pilot plant. A handful of clients have worked on this for 3 or 4 years. Where we're at on our commercialization plan is we've got 2 pilot plants, one in Michigan and one in New Mexico. The bottom down there on the right is a picture of a pilot plant, courtesy CHMM, that we process algal biomass straight out of their fresh pond. And lastly, I'll play the video. Here's the video of our processing plant down in New Mexico.
Department of Energy identifies pilot technology as systems which process half a metric ton of algal biomass per day. In April 2010, SRS Energy completed the field installation of a field-based pre-pilot system at a client site in New Mexico. This first-of-a-kind field pilot wet-fractionation platform continues to receive wet algal biomass from an adjacent algae farm using open pond cultivation techniques. The crude algal oil is recovered from this operation in a batch mode. Design work is underway to create the first pilot-scale continuous flow system, which will be brought online in 2011.
Perfect. Amount of time.
Thank you very much. We have about 2 minutes for questions. Oh, yeah, we have 2. Okay. First one up.
Question. Maybe I missed it, but how much do you process per day of wet biomass?
So we have an optimization bench system that's about 50 grams dry weight, and then we have a pilot plant that's 10 to 15 kilograms dry weight, and then a larger pilot plant that'll do 30 kgs dry weight. The continuous flow unit coming on here at the turn of the year will be 50 kg per hour, continuous flow, ash-free dry weight. We process at about 15%, anywhere from low teens to 20% paste.